The function of mixed-signal ICs and their applications. Mixed-signal integrated circuits, ICs, are semiconductor devices that combine both analog and digital circuitry on a single chip. These ICs process and manipulate both analog and digital signals, making them versatile components in various electronic systems. Here are the key aspects of mixed-signal ICs. Integration, in the context of electronics and technology, refers to the process of combining various components, functions, or systems into a unified whole. It involves the design and construction of complex systems by incorporating different elements to work together efficiently. Integration can occur at various levels, from integrating electronic components into a single chip to creating complete systems that connect multiple devices and subsystems. Here are different levels and examples of integration in electronics and technology. 1. Integration of electronic components. ICs, integrated circuits. The integration of transistors, resistors, capacitors, and other components into a single chip is a prime example of electronic component integration. ICs come in various forms, including analog ICs, digital ICs, and mixed-signal ICs. Microcontrollers and microprocessors, these are integrated circuits that combine a CPU, memory, and various peripherals on a single chip, used for embedded computing applications. ASICs, application-specific integrated circuits. Custom-designed integrated circuits created for specific applications, or a wide range of components and functions are integrated into a single chip. 2. Integration of functions. System-on-chip, SoC, a single chip that integrates multiple functions or subsystems, such as CPU cores, graphics processing, memory, and communication interfaces. SoCs are used in smartphones, tablets, and IoT devices. Mixed-signal ICs. These ICs integrate both analog and digital functions, allowing for the efficient processing of both signal types within a single chip. Sensor fusion, integrating data from multiple sensors, e.g., accelerometers, gyroscopes, and magnetometers, to provide more accurate and comprehensive information, commonly used in robotics and motion tracking systems. 3. Integration of systems. IoT, Internet of Things. The integration of various sensors, devices, and communication systems to create interconnected IoT systems for smart homes, industrial automation, and environmental monitoring. Automotive systems. Modern vehicles incorporate integrated systems for engine control, infotainment, navigation, safety, and more, all working together within a single automobile. Industrial automation, integration of various control systems, sensors, and machinery in factories and plants to automate manufacturing processes. Smart cities, integration of diverse technologies, including traffic management, environmental monitoring, and public services, to improve the efficiency and sustainability of urban environments. 4. Software integration. Software ecosystems, integrating multiple software applications, services, and platforms to provide a seamless user experience. Examples include operating systems, cloud services, and app ecosystems, e.g., iOS and Android. Middleware, software that bridges the gap between different applications or systems, facilitating communication and data exchange. Middleware is often used in enterprise environments for system integration. APIs, application programming interfaces. APIs allow software applications to interact and share data, enabling the integration of various services and applications. Integration in electronics and technology aims to simplify and streamline operations, enhance functionality, improve efficiency, and create more interconnected and versatile systems. It plays a crucial role in the development of advanced and interconnected technologies that drive innovation in various industries. Analog and digital signals are two fundamental types of signals used to represent and transmit information in electronic systems. They differ in terms of their characteristics, representation, and the types of information they convey. Analog signals. Continuous analog signals are continuous and can take on an infinite number of values within a given range. They represent information as a continuously varying voltage, current, or other physical quantity. Waveform analog signals are typically represented as waveforms, with variations in voltage or current over time. These waveforms can be smooth and continuous. Infinite precision, analog signals can have infinite precision. In theory, you can measure an analog signal with any level of detail, making them suitable for representing real-world phenomena with high accuracy. Real-world phenomena, analog signals are well-suited for representing real-world phenomena that change smoothly, such as audio, temperature, and physical measurements. Examples: analog signals include the voltage from a microphone, the temperature from a thermometer, and the voltage across a resistor in a simple circuit. Digital signals. Discrete, digital signals are discrete and can take on only a finite set of values. They represent information as binary values, zeros and ones. Discrete transitions, digital signals transition between discrete voltage levels, such as high, 1, and low, 0, in a stepwise fashion. Limited precision, digital signals have finite precision. They can only represent a limited range of values, and the accuracy depends on factors like the number of bits used. Digital encoding, information is encoded digitally, allowing for robust error correction and noise immunity. It is easier to transmit and store digital signals reliably over long distances or in noisy environments. Examples: digital signals include the binary code of a computer program, the data stored on a hard drive, and the on-off states of electronic switches in a digital circuit. Differences and use cases. Analog signals are often used for representing continuously varying real-world data, like audio signals and sensor measurements. Digital signals are widely used in modern electronics and computing because of their noise immunity and ease of processing. They are fundamental to digital communication, data storage, and the operation of computers and digital devices. The transition from analog to digital technology has been a significant trend in various industries due to the advantages of digital signal processing, error correction, and signal integrity. In practice, digital systems often interface with analog signals using components like analog-to-digital converters, ADCs, to convert analog signals to digital form, and digital-to-analog converters, DACs, to convert digital signals back to analog form. These converters enable the interaction between the two signal types and are essential in many electronic devices and systems. Analog components are electronic devices and building blocks that work with continuous signals, such as analog voltages and currents. These components are essential for processing, amplifying, filtering, and conditioning analog signals in various applications. Here are some common analog components and their functions. Operational amplifiers, op-amps. Function op-amps are versatile integrated circuits used for amplification, filtering, and signal conditioning. They have two input terminals, inverting and non-inverting, and an output terminal. Applications: op-amps are used in various applications, such as amplifiers, voltage followers, filters, and voltage comparators. Resistors. Function: resistors are passive components that introduce resistance into a circuit, affecting the flow of current and voltage levels. Applications: resistors are used for voltage division, current limiting, biasing, and signal attenuation. Capacitors. Function: capacitors store and release electrical energy, influencing the rate of change of voltage in a circuit. Applications: capacitors are used for filtering, coupling, energy storage, and timing in analog circuits. Inductors. Function: inductors store energy in their magnetic fields and resist changes in current flow. Applications: inductors are used in filters, energy storage, and as passive components in analog circuits. Diodes. Function: diodes allow the flow of current in one direction while blocking it in the opposite direction. Applications: diodes are used for rectification, voltage clamping, and signal demodulation. Transistors. Function: transistors can be used as amplifiers or switches in analog circuits. Common types include bipolar junction transistors, BJTs, and field effect transistors, FETs. Applications: transistors are used in amplifiers, oscillators, voltage regulators, and switching applications. Voltage regulators. Function: voltage regulators maintain a stable output voltage regardless of variations in input voltage or load conditions. Applications: voltage regulators are used in power supplies to provide a constant output voltage for analog and digital circuits. Op-amp circuits. Function: op-amp circuits combine operational amplifiers with passive components to perform specific functions like amplification, filtering, and signal processing. Applications: op-amp circuits are used in audio amplifiers, active filters, instrumentation amplifiers, and more. Filters. Function: filters are designed to pass or attenuate specific frequency components of a signal. Common types include low-pass, high-pass, band-pass, and band-stop filters. Applications: filters are used in audio processing, communication systems, and data acquisition for signal conditioning. Oscillators. Function: oscillators generate periodic waveforms or signals at specific frequencies. Applications: oscillators are used in applications such as clock generation, local oscillators in communication systems, and signal synthesis. Analog components play a crucial role in analog electronics, where they are used to manipulate and condition continuous voltage and current signals. These components are essential in applications like audio processing, sensor interfacing, power management, and communication systems. Digital components are electronic devices and building blocks that work with discrete digital signals, which represent information using binary values, zeros and ones. These components are fundamental to digital electronics and play a crucial role in processing, storing, and transmitting digital data. Here are some common digital components and their functions. Logic gates. Function: logic gates perform basic logical operations, and, or, not, XOR, etc., on one or more binary inputs to produce a binary output. Applications: logic gates are the building blocks of digital circuits and are used in digital logic design, arithmetic operations, and control systems. Flip-flops and latches. Function: flip-flops and latches are memory elements that store binary data and can be used for sequential logic and memory applications. Applications: they are used in registers, memory units, and sequential circuits like counters and shift registers. Microcontrollers and microprocessors. Function: microcontrollers and microprocessors are central processing units, CPUs, that execute program instructions, process data, and control various functions in digital systems. Applications: they are used in computers, embedded systems, consumer electronics, and automation applications. FPGAs, field programmable gate arrays. Function: FPGAs are reconfigurable digital devices that contain an array of programmable logic blocks and routing resources. Applications: FPGAs are used for prototyping, digital signal processing, and custom logic implementation in a wide range of applications. Memory ICs. Function: memory ICs store digital data, including both volatile, RAM, and non-volatile, ROM, flash, EEPROM, memory. Applications: they are used in computers, microcontrollers, data storage devices, and various digital systems for data storage and retrieval. Arithmetic logic units, ALUs. Function: ALUs are digital circuits that perform arithmetic and logic operations, such as addition, subtraction, and bitwise operations. Applications: ALUs are an essential component in microprocessors for executing mathematical and logical instructions. Multiplexers and demultiplexers. Function: multiplexers, MUX, and demultiplexers, DeMUX, select one of several input lines and route it to an output or distribute a single input to multiple outputs, respectively. Applications: MUX and DeMUX are used in data routing, data acquisition, and communication systems. Counters and registers. Function: counters are digital circuits that count clock pulses, while registers store data temporarily. Applications: counters are used in applications like frequency measurement and event counting, while registers are essential for data storage and manipulation. Shift registers. Function: shift registers are used to shift data serially from one location to another, making them useful for serial data communication and delay generation. Applications: they are used in data serializing and deserializing, LED displays, and memory units. Decoders and encoders. Function: decoders convert binary inputs into one of several outputs, while encoders perform the opposite task. Applications: decoders and encoders are used in applications like address decoding in memory units and data compression. Digital signal processors, DSPs. Function: DSPs are specialized microprocessors optimized for digital signal processing tasks, including filtering, modulation, and data analysis. Applications: they are used in audio processing, telecommunications, image processing, and control systems. Digital components are integral to modern electronics and computing, enabling the processing, storage, and transmission of digital data in a wide range of applications, from personal computers to smartphones, industrial control systems, and embedded devices. Digital components find application in various fields and industries, playing a crucial role in processing and managing digital data efficiently. Here are some of the key application areas for digital components. Computing and information technology. Microprocessors and microcontrollers power computers, servers, and other computing devices. Memory ICs store data in RAM, ROM, flash, and SSDs. Digital logic gates and ALUs enable arithmetic and logical operations in CPUs. FPGAs and PLDs, programmable logic devices, are used for custom logic implementation and prototyping. Telecommunications. Digital signal processors, DSPs, are used in modems, codecs, and baseband processing for data communication and voice services. FPGAs and ASICs are used in networking equipment for packet processing and data routing. Digital signal processing, DSP. DSPs are employed in various applications, including audio processing, speech recognition, image and video processing, and radar systems. Consumer electronics. Digital components are used in consumer devices like smartphones, tablets, smart TVs, gaming consoles, and digital cameras. Embedded systems. Microcontrollers and microprocessors are the heart of embedded systems used in automotive control units, home automation, industrial control, and IoT devices. Memory and data storage. Digital memory ICs are used in RAM, ROM, and flash memory for data storage in computers, mobile devices, and data storage devices. Digital audio and music production. DSPs and microcontrollers are used in digital audio processing, synthesizers, mixers, and music production equipment. Communication systems. Digital components are used in wireless communication systems, including mobile phones, base stations, and satellite communication. Digital displays. Digital components drive digital displays, such as LED and LCD screens in televisions, monitors, and digital signage. Automotive electronics. Microcontrollers and digital control units are used for engine management, safety systems, infotainment, and navigation in vehicles. Automation and control systems. Digital controllers and PLCs, programmable logic controllers, are used in industrial automation and process control. Scientific and measurement instruments. Digital components are used in test and measurement equipment for data acquisition, data analysis, and signal processing. Aerospace and defense. Digital components are used in radar systems, avionics, navigation systems, and military communication systems. Gaming and entertainment. Digital components drive video game consoles, gaming PCs, and entertainment systems. Medical devices. Microcontrollers and digital signal processing are used in medical imaging, diagnostic equipment, and patient monitoring devices. IoT, Internet of Things. Microcontrollers, sensors, and wireless communication modules are used in IoT devices for data collection and remote monitoring. Power electronics. Digital controllers are used in power management systems, motor control, and power conversion in energy-efficient devices. Security systems. Digital components are used in surveillance cameras, access control systems, and alarms for data processing and control. Robotics. Microcontrollers and digital control systems are used in robots for control, sensing, and data processing. Digital components continue to advance, enabling the development of innovative technologies and applications in numerous industries. Their reliability, scalability, and versatility make them essential in our increasingly digital and interconnected world. Data conversion refers to the process of changing information from one format or representation to another. In the context of electronics and digital technology, data conversion often refers to the conversion of analog signals to digital form, analog to digital conversion, and vice versa, digital to analog conversion. Here are the two main types of data conversion. Analog to digital conversion, ADC. Function, ADC is the process of converting analog signals, which are continuously variable, into digital form, which consists of discrete binary values, zeros and ones. Components, ADCs, also known as analog to digital converters, use various methods to quantize the analog signal and represent it digitally. These methods include successive approximation, delta sigma modulation, and flash conversion. Applications, ADCs are essential in applications like data acquisition systems, audio processing, sensor interfaces, and any scenario where analog data needs to be processed by digital systems. Digital to analog conversion, DAC. Function, DAC is the process of converting digital data, binary values, into analog signals, which are continuously variable over time. Components, DACs, or digital to analog converters, transform discrete digital values into corresponding analog voltages or currents. They use techniques like pulse width modulation, PWM, binary weighted resistors, and R2 or ladder networks. Applications, DACs are used in audio equipment, communication systems, waveform generators, control systems, and wherever digital systems need to generate analog signals. The importance of data conversion lies in the compatibility between the analog and digital domains. Many real-world signals are analog in nature, such as audio, temperature, and sensor readings, while modern electronics primarily operate on digital data. Data conversion bridges this gap and allows analog information to be processed, stored, and transmitted by digital devices. Here's how the process typically works. Analog to digital conversion, ADC. Sampling. The analog signal is sampled at discrete time intervals to capture its amplitude at those points. Quantization. The sampled values are quantized into binary numbers with a certain bit depth, effectively digitizing the signal. Encoding. The binary numbers are encoded and stored for further processing by digital systems. Digital to analog conversion, DAC. Digital input, the digital data, typically binary numbers, is provided to the DAC. Conversion, the DAC converts the digital values into analog voltage levels, reconstructing the analog waveform. Output, the resulting analog signal is available at the output of the DAC for further analog processing or transmission. Data conversion is fundamental to various applications, including audio playback, signal processing, data acquisition, and communication systems. The accuracy, resolution, and speed of ADCs and DACs are critical for ensuring the faithful representation of analog signals in digital form and vice versa. Sensor interfaces refer to the electronic components and circuits that connect sensors to data acquisition systems or microcontrollers, allowing these sensors to communicate with and provide data to digital systems. Sensor interfaces are critical components in various applications, including industrial automation, environmental monitoring, healthcare, and consumer electronics. Here are the key aspects of sensor interfaces. Key functions of sensor interfaces. Signal conditioning. Sensor interfaces often include analog circuitry to condition sensor signals. This may involve amplification, filtering, and analog to digital conversion to ensure accurate data representation. Voltage or current amplification. Some sensors produce low-level signals, and sensor interfaces may include amplifiers to increase the signal strength for further processing. Filtering. Analog filters are used to remove noise and unwanted frequency components from sensor signals, improving the signal-to-noise ratio. Analog to digital conversion, ADC. Many sensors produce analog signals, while digital systems require digital data. Sensor interfaces often include ADCs to convert analog sensor data into a digital format for processing and storage. Digital communication sensor interfaces may include communication protocols, e.g., I2C, SPI, UART, to transmit sensor data to a microcontroller or data acquisition system. Power supply regulation sensor interfaces may provide regulated power supplies to the sensor for proper operation. Data processing some sensor interfaces may include simple processing capabilities, such as calibration or linearization of sensor data. Applications of sensor interfaces. Industrial automation sensor interfaces are used in industrial settings for monitoring parameters like temperature, pressure, and humidity. They play a crucial role in process control and data acquisition systems. Environmental monitoring sensors measuring parameters such as air quality, weather conditions, and water quality often use sensor interfaces to transmit data to environmental monitoring systems. Healthcare sensor interfaces are critical in medical devices like pulse oximeters, blood pressure monitors, and glucose meters, enabling accurate data collection and communication. Consumer electronics many consumer devices, including smartphones and wearables, use sensor interfaces to connect to sensors such as accelerometers, gyroscopes, and ambient light sensors. Automotive in modern vehicles, sensor interfaces connect to various sensors for functions like engine control, airbag deployment, and climate control. Home automation sensor interfaces are used in smart home devices like thermostats, motion detectors, and door/window sensors to enable automation and remote monitoring. Robotics sensors in robots, including proximity sensors, ultrasonic sensors, and cameras, rely on sensor interfaces to communicate with control systems. Energy management, energy monitoring, and smart grid systems use sensor interfaces to gather data from sensors measuring power consumption and generation. Agriculture sensor interfaces connect to soil moisture sensors, weather stations, and other agricultural sensors for precision farming and environmental monitoring. Security systems in security applications, sensor interfaces connect to sensors such as motion detectors, door/window contacts, and security cameras to provide real-time information and alert systems. Sensor interfaces are essential for enabling digital systems to interact with and utilize data from a wide range of sensors. These interfaces enhance the accuracy, reliability, and efficiency of sensor data collection and processing in various applications. Signal conditioning is a crucial process in electronics and engineering that involves modifying, filtering, amplifying, or otherwise preparing analog signals for further processing or conversion into digital data. It ensures that the signals from various sources are in a suitable form for accurate measurement, analysis, and utilization. Here are the key aspects of signal conditioning. Functions of signal conditioning. Amplification signal conditioning can involve amplifying weak signals to make them more robust for measurement or processing. This is particularly important when dealing with sensors that generate low-level analog signals. Filtering is used to remove unwanted noise or interference from the signal. Filters can be designed to pass specific frequency components while attenuating others. Common filter types include low-pass, high-pass, band-pass, and band-stop filters. Scaling adjusts the range and units of a signal to match the requirements of the measurement or control system. This is often necessary to ensure that the signal falls within the dynamic range of the system. Offset adjustment signal conditioning may involve adding or subtracting a fixed offset value to the signal. This can be used to calibrate and zero the signal properly. Linearization is used when a sensor's output is nonlinear, such as in thermocouples. Signal conditioning can transform the nonlinear response into a linear one, making data interpretation easier. Isolation in some applications, it's essential to electrically isolate the signal source from the measurement or control system to prevent ground loops and ensure safety. Isolation amplifiers are often used for this purpose. Conversion in many cases, signal conditioning includes analog to digital conversion, ADC, to prepare analog signals for digital processing. This is common in data acquisition systems. Signal integration and differentiation. Some applications require integrating or differentiating the signal over time, which can be achieved through signal conditioning. Applications of signal conditioning. Sensors. Signal conditioning is frequently used with sensors in various applications, including temperature sensors, pressure sensors, strain gauges, and accelerometers. Data acquisition systems. Signal conditioning is an integral part of data acquisition systems used in industrial automation, test and measurement, and scientific research. Audio and video processing. In audio and video equipment, signal conditioning is used to enhance the quality of audio and video signals. Communication systems. In telecommunications, signal conditioning is used for noise reduction, amplification, and signal equalization. Control systems. Signal conditioning is essential in control systems to ensure accurate feedback and control actions. Environmental monitoring. Environmental sensors, such as those used for weather monitoring or pollution detection, rely on signal conditioning for accurate data collection. Medical devices. Signal conditioning is used in medical instruments like ECG machines, ultrasound devices, and blood pressure monitors to ensure accurate measurements. Power electronics. In power systems and motor control, signal conditioning may involve the measurement of current and voltage signals for control and protection. Signal conditioning ensures that the analog signals generated by sensors and other devices are reliable, accurate, and compatible with the measurement and control systems they interface with. It plays a crucial role in maintaining data integrity and enabling effective signal processing. Power management, in the context of electronics and electrical engineering, refers to the strategies and techniques used to efficiently control and distribute electrical power within electronic devices and systems. The goal of power management is to ensure that electronic devices operate reliably while optimizing energy consumption, extending battery life, and reducing heat generation. Here are the key aspects of power management. Power management strategies. Power conversion. Power management involves converting and regulating voltage levels to match the requirements of different components within a device. This can include voltage step-up, boost, step-down, buck, and voltage inversion, inverting, to provide consistent power to the components. Power supply regulation. Power regulators and voltage regulators are used to maintain stable voltage levels within a specified range, ensuring that electronic components receive the appropriate voltage for reliable operation. Energy harvesting. In some applications, energy can be harvested from the environment, such as solar energy or vibration energy, and converted into electrical power for use in low-power devices. Battery management. For devices with batteries, power management involves monitoring the state of the battery, optimizing charging and discharging, and implementing power-saving strategies to extend battery life. Dynamic voltage and frequency scaling, DVFS in processors and microcontrollers. DVFS allows the adjustment of the operating voltage and clock frequency based on the workload, saving power during periods of lower demand. Sleep and low power modes. Devices can enter low power or sleep modes when not actively in use. In these states, non-essential components are turned off or operated at reduced power levels to conserve energy. Active power management, dynamic management of power resources, including turning components on or off as needed, adjusting power levels, and implementing power-saving algorithms. Components and techniques in power management. Voltage regulators. These components ensure that electronic circuits receive stable voltage levels by converting and regulating the input voltage. Battery chargers. Battery management ICs control the charging process, manage battery health, and prevent overcharging or overdischarging. Energy storage. Capacitors, supercapacitors, and energy storage devices like batteries or fuel cells store and release energy as needed. Switching regulators. Buck and boost converters efficiently regulate voltage levels by rapidly switching power on and off. Clock gating. In digital systems, clock gating can be used to disable clock signals to unused logic, reducing dynamic power consumption. Thermal management. Cooling mechanisms such as heatsinks, fans, and thermal compounds are used to dissipate heat generated by electronic components. Power down modes. Many electronic components and subsystems can be placed in low power or power down modes when not actively used. Applications of power management. Mobile devices, power management is crucial in smartphones, tablets, and laptops to maximize battery life and control thermal issues. Industrial automation. In industrial settings, power management systems are used to optimize energy usage and reduce operational costs. Renewable energy. Power management plays a role in converting and storing energy from renewable sources like solar panels and wind turbines. Electric vehicles. EVs employ advanced power management systems to manage battery charging and power distribution efficiently. Data centers. Data centers use power management to minimize power consumption and reduce cooling costs. IoT devices. Low-power IoT sensors and devices employ power management techniques to extend battery life for remote and energy-efficient applications. Consumer electronics. TVs, gaming consoles, and audio equipment use power management to optimize energy usage during standby and active modes. Efficient power management is critical for reducing energy consumption, prolonging device lifespan, and addressing environmental concerns. It plays a vital role in modern electronics, where energy efficiency and sustainability are of increasing importance. Audio processing refers to the manipulation and enhancement of audio signals using various electronic and digital techniques. It plays a crucial role in a wide range of applications, including music production, telecommunications, speech recognition, and entertainment. Audio processing involves several key functions and technologies. Key aspects of audio processing. Audio signal capture. The process begins with capturing audio signals using microphones or other transducers. The quality of the capture impacts the overall audio processing chain. Analog to digital conversion. ADC analog audio signals are converted into digital form using analog to digital converters, ADCs. This step is essential for processing audio in the digital domain. Digital signal processing, DSP. Once in digital form, audio signals can be processed using various DSP techniques. Common audio processing functions include filtering, equalization, noise reduction, and audio effects. Audio effects processing. Audio effects, such as reverb, delay, chorus, and equalization, enhance or modify the audio signal to achieve desired sonic characteristics. This is widely used in music production and sound engineering. Compression and encoding. Audio data is often compressed to reduce file size and transmission bandwidth. Common audio codecs include MP3, AAC, and FLAC. Transmission and communication. In telecommunications, audio signals are transmitted over various communication channels, including landlines, mobile networks, and the Internet. Speech recognition. Audio processing is used in speech recognition systems to convert spoken language into text or control commands. Music production. Audio processing is integral to music production, involving recording, mixing, and mastering audio tracks. Producers and engineers use a wide range of audio effects and tools to shape the sound. Noise cancellation and enhancement. Audio processing can remove unwanted background noise or enhance specific audio components to improve clarity and quality. Playback and rendering. Audio signals are rendered using loudspeakers or headphones to create the desired auditory experience. Audio analysis and visualization. Audio processing includes techniques for analyzing audio data, such as spectrogram analysis, which provides a visual representation of sound frequencies over time. Common audio processing tools and technologies. Digital audio workstations. DAWs software applications like Pro Tools, Ableton Live, and Logic Pro X provide a range of tools for recording, editing, and processing audio. Audio effects processors. Hardware and software-based audio processors, including equalizers, compressors, and reverbs, shape the sound and add creative effects. Speech recognition engines. Technologies like Google's speech-to-text and Apple's Siri use speech recognition engines to convert spoken language into text. Audio codecs. Codecs like MP3, AAC, and FLAC compress and encode audio data for efficient storage and transmission. Digital signal processors, DSPs. DSP chips or software are used to perform real-time audio processing and effects in audio equipment and systems. Audio libraries and APIs. Developers can use audio processing libraries and APIs to implement audio functionality in software applications. Microphones and transducers. High-quality microphones and transducers capture audio signals accurately, influencing the quality of audio processing. Audio processing continues to advance with the development of technologies like artificial intelligence and machine learning, enabling applications such as voice assistants, automated audio mixing, and immersive audio experiences. It plays a significant role in various industries, from entertainment and communication to healthcare and automation. Wireless communication refers to the transmission of data, voice, or video over radio waves or other wireless electromagnetic signals without the use of physical cables or wires. It is a fundamental technology that enables various forms of wireless connectivity, including mobile and cellular networks, Wi-Fi, Bluetooth, and satellite communication. Here are the key aspects of wireless communication. Key concepts and components of wireless communication. Transmitter. The transmitter is responsible for generating and modulating the information signal into a form suitable for wireless transmission. It often includes a radio frequency, RF, oscillator, a modulator, and amplifiers. Channel. The channel is the medium through which electromagnetic waves travel to carry the wireless signal. It can be air, free space, or a specific transmission medium, such as optical fiber, for optical wireless communication. Receiver. The receiver captures and demodulates the wireless signal to recover the original information. It typically includes an antenna, a demodulator, and amplifiers. Antennas. Antennas are essential components for both the transmitter and receiver, as they transmit and receive electromagnetic waves efficiently. Different types of antennas are used for various applications. Modulation. Modulation is the process of varying the characteristics of a carrier signal, such as amplitude, frequency, or phase, to encode the information signal. Common modulation schemes include amplitude modulation, AM, frequency modulation, FM, and phase modulation, PM. Multiplexing. Multiplexing techniques enable multiple signals to share the same channel efficiently. Techniques include time division multiplexing, TDM, frequency division multiplexing, FDM, and code division multiplexing, CDM. Protocols and standards. Wireless communication systems adhere to specific protocols and standards to ensure compatibility and reliable communication. Examples include IEEE 802.11 for Wi-Fi, Bluetooth, and cellular standards like 3G, 4G, and 5G. Types of wireless communication. Mobile and cellular communication. Mobile networks, such as GSM, CDMA, and LTE, enable voice and data communication for mobile phones and smartphones. Wi-Fi. Wi-Fi, wireless fidelity, is used for local area networking, LAN, and Internet access in homes, businesses, and public areas. Bluetooth. Bluetooth is a short-range wireless technology used for connecting devices like headphones, keyboards, and IoT devices. Satellite communication. Satellites in orbit enable long-distance communication, including television broadcasting, GPS, and global Internet access. NFC. Near-field communication. NFC enables short-range, contactless data exchange between devices, commonly used for mobile payments and access control. RFID, radio frequency identification. RFID uses radio waves to identify and track objects, often used in supply chain management and access control systems. Wireless sensor networks, WSNs. WSNs are used for monitoring and collecting data from remote sensors, commonly used in environmental monitoring and industrial applications. Infrared, IR, communication. IR signals are used for remote controls, data transmission between devices like TVs and set-top boxes, and indoor positioning systems. Applications of wireless communication. Mobile communication enables voice and data communication on mobile devices, including cell phones and smartphones. Internet access. Wireless networks provide high-speed internet access in homes, businesses, and public areas. IoT, Internet of Things. Wireless communication links IoT devices, allowing them to exchange data and operate remotely. Satellite TV and radio. Satellites broadcast TV and radio signals globally. GPS navigation. GPS satellites enable accurate positioning and navigation on a global scale. Emergency services. wireless communication is critical for emergency services such as police, fire, and medical response. Wireless LANs, local area networks used in homes, offices, and public spaces for wireless internet access and device connectivity. Wireless communication is a rapidly evolving field, with ongoing developments in technologies like 5G, which promises faster data rates and lower latency, and the increasing integration of wireless connectivity into everyday devices. It has transformed the way people and devices communicate and has a wide range of applications in various industries. Embedded systems are specialized computing systems that are designed to perform dedicated functions or tasks within a larger system or device. They are characterized by their combination of hardware and software, usually with a strong emphasis on real-time operation and resource constraints. These systems are prevalent in a wide range of everyday devices and applications. Here are some key aspects of embedded systems. Key characteristics of embedded systems. Dedicated functionality. Embedded systems are designed for specific tasks and functions, such as controlling an appliance, monitoring sensors, or managing a piece of industrial equipment. Real-time operation. Many embedded systems operate in real time, meaning they must respond to inputs or events within strict timing constraints. Real-time systems can be classified as hard real-time, strict deadlines, or soft real-time, flexible deadlines. Resource constraints. Embedded systems often have limited resources, including processing power, memory, and storage. These constraints require efficient software and hardware design. Integration. Embedded systems are integrated into a larger system or device, such as a car's engine control unit (ECU), a smart thermostat, or a medical device. Reliability and stability. Embedded systems are expected to be highly reliable and stable. They need to function correctly under various operating conditions and for extended periods. Low power consumption. Many embedded systems run on battery power or have energy constraints, requiring low power consumption to extend battery life. Custom hardware. In some cases, embedded systems use custom hardware or application-specific integrated circuits, ASICs, to optimize performance and power consumption. Components and software in embedded systems. Microcontrollers and microprocessors. The core processing unit in an embedded system, such as an ARM or a PIC microcontroller. Memory. Embedded systems use various types of memory, including ROM, read-only memory, RAM, random access memory, and flash memory. Input-output interfaces. These interfaces connect the embedded system to sensors, actuators, displays, and other devices. Operating system, OS, or real-time operating system. Some embedded systems run a real-time operating system to manage tasks, scheduling, and resource allocation. Others may operate without a formal OS. Software. Application code, custom software code that performs the specific function or task. Device drivers, software that communicates with hardware peripherals. Firmware, software stored in non-volatile memory for booting and basic system operations. Applications of embedded systems. Consumer electronics. Embedded systems are found in devices like smart TVs, digital cameras, washing machines, and microwave ovens. Automotive vehicles use numerous embedded systems for engine control, safety systems, infotainment, and navigation. Industrial automation. Embedded systems control machinery and processes in manufacturing and industrial settings. Medical devices. Embedded systems are crucial in medical devices like pacemakers, infusion pumps, and MRI machines. Telecommunications. Routers, switches, and base stations in telecommunications networks rely on embedded systems. Aerospace and defense. Embedded systems are used in avionics, radar systems, and military equipment. Home automation. Smart thermostats, security cameras, and smart lighting systems use embedded technology. IoT. Internet of Things. IoT devices are built on embedded systems to connect everyday objects to the internet. Gaming consoles. Gaming consoles like Xbox and PlayStation employ powerful embedded systems for gaming and multimedia. Embedded systems have become an integral part of modern life, and their prevalence continues to grow with the advancement of technology and the rise of IoT and smart devices. Their compact, efficient, and task-specific design makes them suitable for a wide range of applications. Automotive electronics refers to the electronic systems and components integrated into modern vehicles to enhance safety, performance, comfort, and convenience. As vehicles have become more complex and computerized, automotive electronics have played a crucial role in shaping the automotive industry. Here are some key aspects of automotive electronics. Key components and systems in automotive electronics. Engine Control Unit (ECU). The ECU is responsible for controlling the engine's operation, including fuel injection, ignition timing, emissions, and performance optimization. Transmission Control Unit (TCU). The TCU manages the operation of automatic and semi-automatic transmissions, ensuring smooth gear shifts and optimal fuel efficiency. Anti-lock braking system (ABS). ABS prevents wheel lockup during braking, improving vehicle stability and control. Airbag Control Unit (ACU). ACUs manage the deployment of airbags and other safety systems during a collision. Electronic Stability Control (ESC). ESC systems help maintain vehicle stability by applying individual brakes and adjusting engine power to prevent skidding or loss of control. Infotainment systems. Modern vehicles come equipped with infotainment systems, including touchscreen displays, navigation, audio systems, and smartphone integration. Advanced Driver Assistance Systems (ADAS). ADAS includes features like adaptive cruise control, lane departure warning, parking assistance, and collision avoidance systems to enhance driver safety. Onboard diagnostics (OBD). Systems monitor the vehicle's performance and report diagnostic information to help identify and address issues. Keyless entry and start. Keyless entry and ignition systems use wireless technology to unlock and start the vehicle without using a physical key. Sensors. Various sensors, including proximity sensors, temperature sensors, and ultrasonic sensors, collect data for various vehicle systems. Telematics. Telematics systems enable vehicle tracking, remote diagnostics, and connectivity features like emergency services and remote vehicle control. Technologies and trends in automotive electronics. Autonomous vehicles. The development of self-driving cars relies heavily on advanced sensors, computer vision, and AI technologies for navigation and decision-making. Electric vehicles (EVs). EVs use advanced battery management systems, motor controllers, and charging infrastructure. Connected vehicles. Vehicles with internet connectivity enable over-the-air updates, real-time traffic information, and cloud-based services. V2X. Vehicle-to-everything. V2X communication enables vehicles to exchange information with each other and with infrastructure, enhancing safety and traffic management. Hybrid powertrains. Hybrid vehicles combine internal combustion engines with electric motors, requiring sophisticated control systems. Lighting technology. LED and adaptive lighting systems improve visibility and safety. Materials and weight reduction. Lightweight materials and smart structures are used to improve fuel efficiency. Environmental and emission control. Automotive electronics play a significant role in reducing emissions through engine control and exhaust treatment systems. Challenges and opportunities. Cybersecurity. As vehicles become more connected, they are vulnerable to cyber attacks. Ensuring the security of automotive electronics is critical. Software complexity. The growing complexity of software in vehicles requires robust development and testing processes. Regulations. Automotive electronics must meet stringent safety and emission regulations, which are subject to change. Integration. Integrating various electronic systems and ensuring compatibility is an ongoing challenge. Automotive electronics have transformed vehicles, making them safer, more efficient, and connected. They continue to evolve with emerging technologies, including autonomous driving, electrification, and advanced connectivity, shaping the future of the automotive industry. Medical devices are a broad category of instruments, apparatuses, machines, or software used for medical purposes to diagnose, treat, monitor, or prevent medical conditions. These devices are designed to aid in the management of patient care and can range from simple tools like thermometers to complex equipment such as MRI machines. Here are some key aspects of medical devices. Types of medical devices. Diagnostic devices. These devices are used for the detection and diagnosis of medical conditions. Examples include blood glucose meters, X-ray machines, and medical imaging equipment like CT and MRI scanners. Therapeutic devices. Therapeutic medical devices are used to treat or manage medical conditions. Examples include pacemakers for heart conditions, insulin pumps for diabetes, and dialysis machines for kidney disease. Monitoring devices. Monitoring devices are used to keep track of a patient's vital signs or health parameters. These include devices like ECG monitors, pulse oximeters, and blood pressure monitors. Surgical instruments. Surgical instruments are used in surgical procedures. These include scalpels, forceps, and laparoscopic tools for minimally invasive surgery. Imaging devices. Imaging devices, such as X-ray machines, ultrasound devices, and endoscopes, enable visualization of internal body structures. Dental equipment. Dental devices include tools like dental chairs, X-ray machines, and dental lasers used in oral healthcare. Laboratory instruments. These devices are used in clinical laboratories for diagnostic testing, including blood analyzers, microbiology equipment, and genetic testing devices. Rehabilitation and assistive devices. These devices, such as prosthetics, wheelchairs, and hearing aids, are designed to assist patients with mobility, sensory, or cognitive impairments. Key aspects of medical devices. Regulation. Medical devices are subject to strict regulatory oversight in many countries to ensure their safety and effectiveness. Regulatory bodies, such as the U.S. Food and Drug Administration, FDA, provide approval and oversight for medical devices. Safety. Safety is a top priority for medical devices. Manufacturers must adhere to rigorous safety standards to minimize risks to patients and healthcare providers. Accuracy. Diagnostic and monitoring devices must provide accurate and reliable results to support clinical decision-making. Durability and reliability. Medical devices are expected to operate reliably over time, often in demanding clinical environments. Ease of use. User-friendly design is essential, as medical devices are often operated by healthcare professionals and, in some cases, by patients themselves. Interoperability. In an increasingly digital healthcare landscape, interoperability is crucial to ensure that medical devices can communicate and share data with other healthcare systems and electronic health records. Applications of medical devices. Hospital and clinical settings. Medical devices are extensively used in hospitals and clinics for diagnosis, treatment, and monitoring of patients. Home healthcare. Many medical devices are designed for home use, allowing patients to monitor their health and manage chronic conditions. Dental clinics. Dental equipment and devices are used in dental clinics for examinations, treatments, and procedures. Laboratories. Clinical laboratories use various medical devices for diagnostic testing, from chemistry analyzers to blood culture systems. Rehabilitation centers. Rehabilitation and assistive devices help patients recover and regain functionality after injuries or surgeries. Pharmacies. Some medical devices, such as blood pressure monitors and glucose meters, are available in pharmacies for consumers to purchase. Medical devices play a critical role in modern healthcare, helping healthcare providers diagnose, treat, and monitor patients. The continued advancement of technology and innovation in the field of medical devices has the potential to improve patient care and outcomes. IoT, Internet of Things, devices are physical objects or systems that are embedded with sensors, software, and other technologies to connect and exchange data with other devices and systems over the Internet. These devices are a fundamental component of the broader IoT ecosystem, enabling the collection and exchange of data for various applications. Here are some key aspects of IoT devices. Key characteristics of IoT devices. Connectivity. IoT devices are designed to connect to the Internet or other devices, enabling data exchange and remote control. Common connectivity options include Wi-Fi, cellular, Bluetooth, and LPWAN, low-power wide area network. Sensors. IoT devices are equipped with various sensors to collect data from their environment. These sensors can measure factors like temperature, humidity, pressure, motion, light, and more. Data processing. IoT devices often have embedded microcontrollers or processors to process the data collected from sensors. This processing can include data aggregation, analysis, and decision-making. Communication protocols. IoT devices use various communication protocols to transmit and receive data. These protocols can be standardized, e.g., MQTT, HTTP, or proprietary, depending on the application and the manufacturer. Remote monitoring and control. IoT devices enable remote monitoring and control of physical objects or systems, allowing users to access data and make adjustments from anywhere with an internet connection. Power efficiency. Many IoT devices are designed for low power consumption, allowing them to operate on batteries or energy harvesting methods for extended periods. Scalability. IoT ecosystems can consist of thousands or even millions of devices. IoT device architecture must be scalable to accommodate the growth of connected devices. Types of IoT devices. Smart home devices. Examples include smart thermostats, security cameras, smart lighting, and voice-activated assistants. Wearable devices. Wearables like fitness trackers, smartwatches, and medical devices are equipped with sensors and connectivity for health monitoring and personal data collection. Industrial IoT, IIoT devices. These devices are used in industrial settings for asset tracking, predictive maintenance, and process optimization. Environmental monitoring devices. IoT sensors are used for monitoring air quality, weather conditions, soil moisture, and water quality. Healthcare devices. Medical IoT devices include remote patient monitoring, medication adherence systems, and telehealth solutions. Smart city infrastructure. IoT devices are used for smart street lighting, waste management, traffic control, and public safety. Agricultural IoT, agri-tech devices, sensors and monitoring equipment are used in precision farming for soil analysis, crop health, and livestock management. Smart energy devices. These include smart meters, energy management systems, and devices for optimizing energy consumption. Applications of IoT devices. Home automation. IoT devices enhance convenience and energy efficiency in smart homes by controlling lighting, heating, cooling, and security systems. Healthcare. Remote patient monitoring and telehealth solutions improve patient care and enable healthcare providers to gather data for diagnosis and treatment. Industrial and manufacturing. IoT devices are used for predictive maintenance, process optimization, and asset tracking in factories and industrial settings. Agriculture. IoT sensors and devices help farmers optimize crop yields, reduce resource usage, and monitor livestock health. Smart cities. IoT devices support various urban initiatives, including traffic management, waste collection, and environmental monitoring. Environmental conservation. Environmental monitoring devices assist in collecting data on air and water quality, as well as climate and ecosystem health. Energy management. Smart meters and energy management systems help consumers and utility companies monitor and control energy consumption. IoT devices play a vital role in the digital transformation of industries and have the potential to improve efficiency, reduce costs, and provide valuable data for decision-making in various sectors. Their widespread adoption is contributing to the growth of the IoT ecosystem. Power electronics is a specialized field of electrical engineering that deals with the conversion, control, and management of electrical power using electronic devices and circuits. It plays a crucial role in various applications, including power generation, distribution, and consumption. Power electronics focuses on the efficient conversion of electrical energy from one form to another, such as AC to DC, DC to AC, and changing voltage levels. Here are key aspects of power electronics. Key aspects of power electronics. Power conversion. Power electronics is primarily concerned with converting electrical power from one form to another. This includes conversion between alternating current, AC, and direct current, DC, voltage level conversion, and frequency conversion. Switching devices. Power electronic circuits use semiconductor devices like diodes, transistors, thyristors, and insulated gate bipolar transistors, IGBTs, to control the flow of electrical current. These devices operate in a switching mode, changing their state to control the output power. Control and regulation. Feedback control systems are often used to regulate the output of power electronic converters. These systems ensure that the output voltage and current meet specific requirements, such as inverter output voltage regulation in renewable energy systems. Applications. Power electronics is employed in a wide range of applications, including motor drives, renewable energy systems, solar and wind power, electric vehicles, EVs, uninterruptible power supplies, UPS, industrial automation, and more. Efficiency. One of the primary goals of power electronics is to achieve high efficiency in energy conversion. This is critical for applications where energy conservation and reduced losses are essential. Power factor correction. Power factor correction techniques are used to improve the power factor of electrical loads, making them more efficient and reducing reactive power consumption. Switching frequencies. The switching frequency of power electronic devices and circuits can vary, with high-frequency operation in the kilohertz or megahertz range, offering benefits such as reduced size and weight of components. Common power electronic devices. Diodes. Diodes are used in rectifier circuits to convert AC to DC. They allow current flow in one direction. Transistors. Bipolar junction transistors, BJTs, and field effect transistors, FETs, are used for switching and amplification in various power electronic applications. Thyristors. Thyristors, including silicon-controlled rectifiers, SCRs, and gate turn-off thyristors, GTOs, are used for high-power switching in applications like motor drives and power converters. Insulated gate bipolar transistors, IGBTs combine the advantages of MOSFETs and BJTs, making them suitable for high-power applications. MOSFETs, metal oxide semiconductor field effect transistors. MOSFETs are often used for high-frequency, low to medium power switching applications. Applications of power electronics. Motor drives. Power electronics control the speed and torque of electric motors in various applications, including industrial machines and electric vehicles. Renewable energy. Power converters are used in wind turbines and solar inverters to interface renewable energy sources with the power grid. Power supplies. Switched mode power supplies, SMPS, convert AC power to regulated DC power for electronic devices and equipment. Electric transportation. Power electronics are crucial in electric vehicles, EVs, and hybrid electric vehicles, HEVs, for motor control and battery management. Uninterruptible power supplies. UPS systems use power electronics to provide backup power during outages, ensuring continuous operation of critical equipment. Aerospace and space exploration. Power electronics are used in satellites, spacecraft, and aircraft for power conversion and control. Power electronics is an essential technology that enables efficient energy conversion and plays a pivotal role in modern electrical systems and energy management. Its continued development is essential for improving energy efficiency and the integration of renewable energy sources.